Continuity at a point. Continuity at a point only exists if several conditions are met. The left-hand limit and the right-hand limit must exist and equal each other. Additionally, the limit must equal the point f of c. If the function is not continuous at f of c, either because the one-sided limits do not equal each other, or because f of c does not exist, the function is said to be discontinuous at this point. Here's an example. Determine whether the function is continuous at the given point. So whether f of x is continuous at x equals 4, at x value 4. So let's try to determine this by plugging in 4 for x. So we get 4 squared plus 8 times 4 minus 16 divided by 4 minus 4. We can see that f of 4 equals 0 over 0. This result is indeterminate. That means that there's a point of removable discontinuity at x equals 4, and the function is not continuous at x equals 4. Another example. Determine whether the function is continuous at the given point. Let's try to figure this out. So, the limit of the function 6x squared minus 4x as x approaches 3 from the left equals 42. The limit of 6x squared minus 4x as x approaches 3 from the right also equals 42. Therefore, the limit of f of x as x approaches 3 equals 42. F of 3 equals 6 times 3 squared minus 4 times 3. F of 3 equals 42. From this, we know that the limit exists. From this bit, we know the point exists. Combining these two notions, we figure out that since f of 3 equals the limit of f of x as x approaches 3, f of x is continuous at the x value of 3. So in this example, we're going to look at a series of graphs and determine whether they are continuous or discontinuous. And if they are discontinuous, we're going to name the type of discontinuity. So in this graph, we see a point at 0, 1, and we know the function f of x equals x plus 1. From the graph, there is no reason to believe it would be not continuous, so we determine that it is continuous at x equals 1 and over the entire domain of the function seen here in the graph. This next one, we see it's a broken graph. We see a point at 2, 1, which means there's no point here at 2, negative 1. And what can we say about this graph? We can say it's a jump graph, and because of that, we know that it's a non-removable discontinuity at x equals 2. Okay. In this graph, we see that from the as x approaches 0 from the left and the right, we see that on both the left and the right, the limits are approaching infinity. However, this does not mean it's continuous even though the left and right limits exist, because, as we said earlier, f of c must equal the limit. And here f of c is as if we replace x with 0, we see that we get 1 over 0, which is undefined. And the result of this is discontinuity of the infinite variety.